In this video, we are going to focus on applications of normal distribution. In the last section, we saw standard normal distribution where mean was 0 and standard deviation was 1. In this section, we'll focus on the normal distribution where mean is not going to be 0, mean is different from 0, and standard deviation is different from 1. We will standardize the scores. We will convert our data values into z-scores, and then we'll still be able to use the z-score tables from the last section. Okay, the z-score formula we talked about in chapter 3 earlier. So here's the z-score formula. Remember that. Always round the z-scores to 2 decimal places. You can also use a calculator. I prefer Casio 991EX or StatCrunch to find the probabilities using normal distribution. Okay, so z-score is equal to x is the data value. So data value minus the mean divided by standard deviation. Okay, so in this section, we're going to be dealing with two kinds of problems. One's where you're looking for the area using z-scores. Area and probability is the same thing. Okay, area and probability correspond to each other. So they're the same things. One type of problems we will be looking for the area to the left of z-score, to the right of z-score, in the middle of two z-scores. In that case, we'll have to convert data values to z-scores and then find the corresponding areas or probabilities. The second kind of problems, we will be given the z-score or the data value, and we'll have to find the area or you'll have to find the z-score or data value. We'll be looking for the z-score or data value, and we'll be given the area and probability. In that case, we'll first find the z-score and then proceed to find the data value. Couple of examples worked out. We will go ahead and discuss this. Height of men are normally distributed. The mean is 69 inches and standard deviation is 2.8 inches. Is 72-inch airplane door height high enough for most men to walk without bumping their head? What percentage of men can fit through a 72-inch doorway? Okay, so the mean is given to us. The mean is 69. Standard deviation is 2.8. So we're trying to figure out what percentage of men can walk through a door that is 72-inch high. So I'm going to find the area that is less than, to the left of 72-inch in the normal curve, or whatever corresponding z-score is for 72-inch on the standard normal curve. So first step, I'm going to convert the z-score, 72 into the z-score. So that's the data value minus mean divided by standard deviation. So x minus mean divided by standard deviation, that's the z-score formula. Turns out to be 1.0714, and we always round to 2 decimal places. So now we're looking for probability or the area to the left of 1.07, because everyone who's shorter than 72 inches will be able to walk through, and somebody who's taller than 72 inches will be not able to walk through. So probability for the z less than 1.07. Now this is the z-score, so we'll have to read the table. You can use the calculator, see a separate video how to use the Casio 991 calculator, or another video on StatCrunch, how to use StatCrunch. But in this section, I'm going to be focusing on the tables that come with the textbook, and each homework problem will have these tables attached to the problem. Okay, so z less than 1.07, look for positive 1.07. So 1.0 here, and 7 is in this row. Okay, keep going down and see wherever they intersect, and that's going to be our z-score here. So there we go, 0.8577 is the probability or area. So in the body of this table, we have probability or area, and on the top row and the side column, left side column, that comprises your z-scores. Okay, so 0.8577 is the area. That means if we convert it to the percentage from decimal, that would be 85.77%, which is most men. No, most men, 85% of the men will be able to walk through that door, or 86% approximately. And that's most men, okay, to answer the question. Second example, a hospital requires the newborn babies born weighing less than 2,700 grams receive special treatment. What percentage of newborn babies will require special treatment? assume the birth weights are normally distributed. So anytime you see the normally distributed word or symmetric curve or bell curve, we can use these standardized z-score tables. So mean is 3570 and the standard deviation is 500. And we are told that kids who weigh less than, babies who weigh less than 2,700 grams will need special treatment. So we're trying to find out how many babies do weigh less than 2,700 grams. So let's go ahead and find the z-score for 2,700, which will be data value. Z-score is data value minus mean divided by standard deviation. Turns out to be negative. Negative means this is below average. We've talked about z-score 0 is for the mean. Any value that has a positive z-score is above your mean. Any value that's got a negative z-score is below your mean. Okay, so z less than negative 1.74. We're looking for the area to the left of negative 1.74. Let's look at the table again. It's also important to keep in mind this table gives me area to the left. This picture tells me it talks about area to the left of the z-score. And now we're looking for area to the left of negative 1.74. So let's look at negative 1.74 here. Negative 1.7 and 4 turns out to be 0.0409. That's the area to the left, 0.0409. The z-scores can be negative or positive, but the probabilities or areas can never be negative or positive. So it turns out to be 4.09%. So about 4% of the babies will need the special treatment. If we change this to percentage, so 4.09, which is about 4% of the babies will need special treatment. Okay, now there's another part added to the problem. This is part B, and that's going to be something different we haven't talked about. This is the second kind of problem you're going to have to deal with. You will be given the area or probability, and we'll be looking for the data value. So our first goal will be to find the z-score. Once we find the z-score, we will be looking for the data value. Here's the part B. Suppose the hospital plans on giving special treatment to lightest 3%. Okay, lightest 3%. Lightest 3% means lightest 3%. This is the area. Lightest 3% of the babies. What birth weight separates healthy babies from those needing special treatment? We're given the probability. We're looking for the data value now. We're looking for the weight now. We're given the probability. So anytime you're given the probability or area, we're going to look in the body of the table. And also think about, are you going to look for, is this going to be a negative z-score or positive z-score? Negative z-score or positive z-score? Well, this is going to be a negative z-score. It's below your mean. So I'm going to look in the negative z-scores, and I'm going to look for this number in the body of the table. In the body of the table, my numbers are actually given me to 4 decimal places. So sometimes you won't find this exact number. So we'll look for the one that's closest, 0.0300. Okay, so let's go ahead and look for this in the body of the table, 0.0300 or something that's closest, 0.03. 0.01, 0.02. I think this is the closest. And the corresponding z-score will be negative 1.88. 1.88. We get negative 1.8 from here and 0.08 from there. So that turns out to be negative 1.88. So the z-score that has 0.03 area to the left is negative 1.88. So that's the z-score. And now we're going to just plug it into the z-score formula, because we just found the z-score, which is data value minus the mean divided by standard deviation. Negative 1.88 equals data value is what we're looking for. We are given the mean and we are given the standard deviation. To solve it, I'm going to multiply both sides with 500 first so that I can get rid of it from the right hand side. and that leaves me negative 940 equals x minus 3570. X comes out to be 2630. So babies whose weight is less than 2630 grams will need special treatment. Okay, they should plan on treating a higher percentage of at least 4%, because we saw that in the last part of this problem that 4% babies will fall in the range of, you know, unhealthy weight or low birth weight. Okay, example number 3. Read it in the notes. It's worked out. I'm leaving it for you. And example number 4 as well is worked out. Read it in the notes. I'm going to move on to example number 5. We will do it together. Do a couple of examples together. The weight of adult male beagles are normally distributed with a mean of 25 pounds and a standard deviation of 3 pounds. I also want to point out that if you're using the tables or you're using the StatCrunch, your answer will be more accurate when you're using the StatCrunch, because table rounds the values to 4 decimal places, the probabilities to 4 decimal places, but StatCrunch will give you more accurate. It can be slightly different, but both answers should be correct when you plug them into the homework system, MyMathLab. Both answers should be accepted because they have some tolerance, plus minus, within to certain decimal places. The weight of adult male beagles are normally distributed with a mean of 25. So the mean is 25 and the standard deviation is 3. A beagle is randomly selected. Find the probability the beagle's weight is less than 24 pounds. So we want to find probability of the weight less than 24 pounds. So I need to convert the z-score 24 into the z-score. So I'm looking for area to the left of certain z-score. What is a z-score? Let's go ahead and convert 24 into the z-score. Mean z-score is data value minus mean divided by standard deviation. This case data value is 24, mean is 25, and standard deviation is 3. That z-score turns out to be negative 0.3333, negative 0.3333, and we round it to 2 decimal places, so negative 0.33. We're looking for the area to the left of negative 0.33 on the z-score table. So how much area is to the left of negative 0.33 or negative 0.33? Let's look at negative 0.33, and area to the left is what we're looking for, negative 0.33. Negative 0.3, and here we go, coming this way. Turns out to be 0.3707. So 0.3707. 0.3707, negative 0.33. Let me check one more time. So, okay, 24 minus 25 divided by 3 is negative 0.33, and we're looking for the area to the left of negative 0.33, negative 0.33. Okay, so 0.3707. That's what I got from the table. Again, if you use StatCrunch, your answer will be more accurate. It could be slightly off in terms of the decimal, but that's what I'm getting from this table. And I'm going to say about 37.07% of beagles will weigh less than, there's 37.07% chances, probability of a beagle weighing less than 24 pounds is probability that a randomly selected beagle weigh less than 24 pounds is 37.07% or 0.3707. We always leave probability in terms of decimal. Okay, 0.3707, or we can say 37.07% chances that this is going to happen. Let's look at part B. The the beagle's weight is between 23 and 26 pounds. So what's the probability that the weight lies between 23 pounds and 26 pounds? So I need to convert both of these into the z-scores and find the area in between those z-scores. Okay, so let's go ahead and find the z-score for 23. 23 minus 25 divided by 3, and that's going to be went too far on the calculator. That's negative 0.66, negative 0.6666. So it's repeating. So this is going to be negative 0.67. Okay, rounded to 2 decimal places. Now z-score for 26 is 26 minus 25 over 3. That would be 1 divided by 3. That would be 0.33. 0.33. Again, we're going to round to 2 decimal places. So we're looking for the area between negative 0.67 and 0.33 on the z-score table. So what we can do is we can find the area to the left of 0.33 and find the area to the left of negative 0.67 and subtract the two areas, because 0.67 is about here. I'm just using estimate, and 0.33 is about here, and we're looking for area in the middle. So what we can do is we can find the entire area to the left of 0.33 and subtract the area to the left of negative 0.67, and the difference is going to be the area in the middle, or probability. Okay, so 0.33 area to the left is 0.33, 0.6293. Okay, so 0.6293, and area to the left of negative 0.67, negative 0.67 is 0.2514. Okay, so coming down, 0.2514, 0.2514. So 0.6293 minus 0.2514 turns out to be 0.3779, 0.3779. So 0.3779. So we can say probability that you randomly select a beagle and the beagle weighs between 23 to 26 pounds is 37.79%, or approximately 38% chances that you randomly select a beagle and the beagle will weigh between 23 pounds to 26 pounds. Okay, let's look at part C now. For part C, the beagle weighs more than 29 pounds. What's the probability that you randomly select a beagle and it weighs more than 29 pounds? So again, first of all, I'm going to change the 29 into z-score. 29 minus 25, 29 minus 25 divided by 3 turns out to be 1.33, 1.3. What's the probability that the weight is more than 29, or the probability, the area to the right of z-score 1.33. Now we are looking for area to the right. Okay, be clever, be smart. Your table only gives you area to the left, so we know the entire area is 1. The total area under the normal distribution curve is 1. So we can subtract the area to the left. We can do 1 minus area to the left. That would give us the area to the right. So area to the left of 1.33 is 1.33, 0.9082, yep, 0.9082. And when we subtract 0.9082, 1 minus 0.9082 is going to give us area to the 0.0918. So this is going to give me area to the right of 1.33. Again, if you randomly select a beagle, probability that it weighs more than 29 pounds is 9%, approximately 9% chances, or 9.18% probability that the beagle's weighs more than 29 pounds if you randomly select a beagle out of that population. Okay, here's example number 6. Lots of parts here. Again, the process is going to stay the same. The test scores for exam in statistics class have a mean of 78 points and a standard deviation of 9 points. A student is randomly selected, okay, assuming the scores are normally distributed. So whenever I see this, I can tell that I'm dealing with the normal distribution. Scores are normally distributed. What's the probability that students scored more than 95? So for part A, we want the score to be more than 95. So first step is to find the z-score for 95. I see 95 is above average. So I'm going to expect a positive z-score. So 95 minus 78 divided by 9 is equal to 1.88888, and if I round it, it would be 1.89. We always want to round the z-score to 2 decimal places. Now we are looking for the area to the right because we're seeing more than, okay? So we are looking for probability of the area, probability or the area to the right of z-score 1.89. Well, I do know my table doesn't give me area to the right. If I'm looking for area to the right, I have to do 1 minus whatever I see in the table, whatever area I see in the table. So area to the right of 1.89 is, let's see, what does the table tell me? 1.89, 1.89, yep, 0.9706. So 0.9706. 1 minus 0.9706 turns out to be 0.0294. 0.0294. Okay, so 0.0294 is, so we can say probability of randomly selecting a student who scored more than 95% is about 2%. So 2%, 2.9%, or about 3% probability that you randomly select a student, low chances that you randomly select a student. Always interpret your solution, write it in a complete sentence after you're done. I'm not doing that to save time, but write the complete sentence. The probability of randomly selecting a student who scored more than 95 is 2.9% approximately. Part B, less than 30. Less than 30 means we're looking for the score to be less than 30, and that means we're looking for area to the left of the z-score. What's the z-score for 30? So 30 take away 78 divided by 9. That's going to be the z-score, negative 5.33. So negative 5.33. Okay, so we want to find this area to the left of z-score, negative 5.33. If you look here, you wouldn't see negative 5.33. It's beyond our table's range, because if you recall, we've also talked about empirical rule. We have 68% of the area within 1 standard deviation, 95% of the area within 2 standard deviations. So this is mu plus sigma, mu minus sigma, and then 95% within 2 standard deviations, and 99.7% areas within 3 standard deviations. So beyond 3 standard deviations, there's very, 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 very little, actually no area. And if you look on the bottom of the table, it doesn't say here, but we can see, we can really just see here. Negative, anything that's beyond your table, we would say, because negative 5.33 is about here, and area to the left is going to be almost 0 here, okay? So area to the left will be almost 0. Anything that's beyond your table, the area will be 0. So we can say chances of selecting somebody who's scored less than 30 will be 0 in this case. Okay, next example. What's the chance of selecting somebody whose score is between 80 and 90? So now we're looking for somebody with the score of 80 and 90, which is going to be, find the z-score, 80 minus 78 divided by 9, 90 minus 78 divided by 9. Find the z-scores for both. Okay, 80 minus 78 divided by 9. That's 0.22. And if I go back and change this to 90, that is going to be 1.33. So we're looking for the area in between 1.33 and 0.22. 0.22 and 1.33. Again, what we have to do is we can find the area to the left of, because here's my curve. 1.33 is here and 0.22 is here. We're looking for area in the middle. So we'll find area to the left of 1.33 and subtract the area to the left of 0.22 from it. Okay, so that's going to give me area to the left of 1.33. 1.33 is 0.9082. Yep, 0.9082. And area to the left of 0.22 is, okay, 0.22. 0.5871. And now find the difference. So 0.9082, 0.5871 turns out to be 0.3211. Okay, again, if you use your calculator or if you use StatCrunch, it might give you answer 0.3212, which would be still acceptable by MyMathLab, okay, because it does have some tolerance level within the answer itself. So 0.3211, about 32.11% chances that you randomly select somebody and their score would lie between 80 and 90. Okay. Part D, if there are 70 students in the class, about how many will receive between 90 and 95 points? Okay, so first I need to find out what is the probability of somebody having their score between 90 and 95. I need to first score between 90 and 95. I need to first find the z-scores for 90 and 95. For 90, we just found out in the last problem, 1.33. For 95, it's 1.8. I think we did that in the first problem, 1.89. Okay, 1.89. What's the probability or the z-score? So I found both the z-scores. 1.33 less than 1.89. So what's the area that lies between 1.33 and 1.89? Again, we'll find the area to the left of 1.89 and then find the area to the left of 1.33 and subtract the two areas. Okay, what's the area to the left of 1.89? Let's check our table. 1.89 is 0.9706. We did it in the earlier problem too. 0.9706. Area to the left of 1.33 is 0.9082. We also did it in the previous problem. So 0.9706 minus 0.9082. It turns out to be 0.0624. 0.0624. So 0.0624. So that's approximately 6.2%. 6.2%. Probability of randomly selecting somebody whose score is between 90 and 95 is 6.2%. Now, if there's total 70 students, how many students will receive between 90 and 95? What is 6.2% of 70 students? So 6.2% of 70 will be point. Turns out to be 4.34, which is going to be, for number of students, number of people, we always round up. So we would say 5 students. So 5 students scored between 90 and 95. Here's another example, number 8. The weight of men are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Okay, what weight separates the lightest 99.5% of men from the heaviest 0.5 round to the one decimal place? So this is my mean and this is my standard deviation. And we're looking for the weight now. We're not looking for the we're not looking for the probability. We're looking for the data value because it says what weight separates. We're not looking for the area, not looking for probability. We're looking for the weight, which is the data value. So first step is to find out the z-score. What z-score has the lightest 99.5%? So what z-score has 0.9950? Because if I change 99.5% into a decimal, that's 0.9950. What z-score has 0.9950 area to the left? So what z-score has 0.9950 area to its left? So let's look in the body of the table. I know it's going to be a positive z-score because I'm all the way above mean. To the left of mean, I have 50% of the data value. So, or 50% of the area, and this is way above my mean. So I'm going to be looking at the positive z-score body of the table, and I'm looking for this number, 0.9950, or something closest, okay? 0.9950. Let's check 0.9950, 9945. So here we are. 0.9949 and 0.9951. They both are equally away from 0. We cannot say one is closer. One is closer to 0.9950 because my number was 0.9950. So they both are equally away. I'm going to have to find the average. So my z-scores are 2.56 and 2.57 and 2.58. Right, yep. 2.57 and 2.58, and the average of 2.57 and 2.58 would be 2.575. Okay, 2.575. Because we can do 2.57, we can do 2.57 plus 2.58 divided by 2. So that's 2.57 plus 2.58 divided by 2. That's how I'm going to be able to get the average of these two, which is 2.575. And that's my z-score, okay? That is the z-score that lies here that has 0.995 area to the left, okay? So 2.575 is the z-score. Once we know the z-score, finding the data value is not a big deal because we knew the z-score formula is data value minus mean divided by standard deviation. So z-score is 2.575 equal to the data value is what we're looking for. Mean is 172, standard deviation is 29. To solve this equation, I'm going to first multiply both sides of 29 to get rid of the denominator. 29 times 2.575, it is going to be 74.675. 74.675 equals x minus 172, and x would be 172 will be added to the other side. Turns out to be 246.675. Yep, 246.675. Or we can say approximately 246.7 pounds. So 246.7 pounds or approximately 246.7 pounds is the weight that will separate the heaviest 0.5% men from the lightest 99.5% men. Okay. All right. So anybody who weighs more than 246.7 pounds will be in the top 5% on the heavier side. Anybody who weighs 246.7 or less would be lighter 99.5% range. Find P15. P15 is 15th percentile. 15th percentile means what weight has 15% of the values below it. 15% is the area here. So 0.15, I'm just writing it as 4 decimal places. So 15%, what weight has 15%, what is the weight that 15% of men weigh less than that and other 85% men weigh more than that? So that's what we're looking for. So to find the weight, first we need to find the z-score, then use the z-score formula to find the data value. So my goal is to look for what is the z-score what is this z-score that has 15% area to its left. Again, my table does give me area to the left, so that part is nice and easy. I should be looking into the negative z-scores because this is way below my average. Average is 50% in the middle, and this is 15%, so kind of on the left-hand side. So negative z-scores, okay? Look in the negative z-score table, 0.1500 in the body of the table, 0.15 in the negative z-scores, okay. 0.15, so it's 13. 0.1587 is here, 0.1587, 1515.1492. Which one seems closer? Well, to me it looks like this one is closer to 0.1500 because my z-score was 0.1500. 0.1492 seems closer than 0.1515. So negative 1.04 is my z-score. Okay, negative 1.04 is my z-score in this case. No highlighter, negative 1.04 is the z-score. So z is data value minus the mean divided by standard deviation. We're looking for the data value. We already know the mean, 172. We already know the standard deviation. Standard deviation is 29. Let's go ahead and solve it and find the data value. I'm going to multiply both sides with 29. So 29 times 1.04 turns out to be 30.16. X minus 172. Okay, from here x turns out to be 172 plus 30.16. That is going to be 202.16. 202.1. Something does not look right here. Let me double check. So 29 times negative, that doesn't look right. Let me recheck my work. So 29 times negative 1.04. So 1.04 times 29 is 30.16 negative. Okay, awesome. Now from here, when I'm isolating the x, so I'm going to add 172 to both sides. 172 minus 30.16. So 172 minus 30.16 turns out to be 141.84. 141.84. So approximately 142 pounds is the P15 or 15th percentile. That means about 15% of the men weigh less than 142 pounds and 85% of the men weigh more than 142 pounds. Okay. Now we're looking for Q3, which is third quartile. It's same thing as 75th percentile. Third quartile is same thing as 75th percentile. So I'm looking for the weight separating top 25% from others, or bottom 75%. It would be the same thing. So area to the left is 0.7500. Area to the right is 0.2500. It's easier to look for area to the left. So I'm going to look in the body of the table. Again, it's going to be a positive z-score because we're talking about 75% area to its left. So that's a positive z-score because mean has 50% area to the left. So let's look in the body of the table, 0.7500. Clean up the old mess, 0.7500. Okay, 0.7500 in the body of the table for positive z-scores. Somewhere right here, 0.7517, 0.7486. Which one seems closer? Well, again, if you're using StatCrunch, it's going to give you more accurate, correct answer. I'm not using StatCrunch, I'm using the table, but these answers should be also acceptable by MyMathLab. Again, they do have a tolerance error input into the answers, okay? So 0.7500, I think 0.7486 is the closest based on the table. So 0.67 is my z-score, okay? This is z-score 0.67. And I already know that z-score is data value minus the mean divided by standard deviation. The data value is what we're looking for. The mean is 172, standard deviation is 29. So to solve this equation, first step is to multiply both sides by 29. 29 times 0.67 turns out to be 19.43 equals x minus 172. X turns out to be 172 plus, that's 191.43. 191.43. So approximately 191.4 pounds. So approximately 191.4 pounds. So this is the weight that separates lighter 75% men from the heavier 25% men. Okay. Next example. This is going to be our last one, and there's lots of parts here. So let's see how many we can get through in this video for part A. Now, you can do all the problems. They're going to be very similar as long as you understand what we're looking for. So two kinds of problems we are dealing with. One kind, you might be given the z-score and then you're looking for, or the data value. You might be given the z-score. So just to summarize, you might be given the z-score or data value, and you're looking for probability or area, either to the left or to the right of the z-score or in between two z-scores. The second kind of problem is you're given the probability or area and you're looking for the data value. So for that, you first have to find the z-score, and then from there use the z-score formula to find the data value. So let's see this example. If IQ is normally distributed with a mean of 100, okay, so mean is 100 for IQ and the standard deviation is 15. Calculate the probability of finding a genius IQ greater than 130. Okay, what's the probability of finding IQ greater than 130? Now my goal is to convert the 130 into z-score. Z-score is data value minus the mean divided by standard deviation, which is 30 divided by 2 is 2.00. What's the area to the right of 2.00? We're looking for somebody whose IQ is greater than 130, right? So to the right of these 2.00, I'm going to the table 2.00. I do know my table doesn't give me area to the right, it actually gives me area to the left. So I can subtract, I can do 1 minus whatever is area to the left, that would be the area to the right. So 2.00 is here, 0.9772. That is the area to the left. So if your 2.00 is here, this is the z-score that has 0.9772. 0.9772 area to the left, but we want area to the right because we're looking for greater than, not to the left. So 1 minus 0.9772 is 1 minus 0.9772. Turns out to be 0.0228. 0.0228. Okay, 0.0228. That is going to be, so probability of randomly selecting somebody whose score is more than 130 is about 2.2%. So very low chances that you randomly select an individual from this crowd and their IQ will be greater than 130. So 2.2% is the probability. Low probability, right? Let's look at part B now. Calculate the probability of average intelligence between 90 and 110. So average intelligence, again, we always have to convert. So we're looking for IQ between 90 and 110. We need to find the z-score for 90 and 110, and that's going to be negative 0.67 and positive 0.67. Probability, the area between negative 0.67 and positive 0.67. What's the area between negative 0.67 and positive 0.67? So let's look for that. Area to the left of positive 0.67, because here's your negative 0.67 and here's your positive 0.67, because your mean 0 is in the middle. We're looking for area in the middle. So we can find the area to the left of positive z-score and find the area to the left of negative z-score and subtract them, because if you find area to the left of 0.67, it's going to give you all that area. And if you find area to the left of negative 0.67, that's going to give you all this area. And if we subtract them, we have the difference. We have the area in the middle. So positive 0.67, let's find that. 0.67, positive 0.6. Is it 0.7486? Yep, looks like 0.7486. 0.7486. And now let's look for the area to the left of negative 0.67. Negative 0.67. 0.2514. No highlighter. 0.2514. Go ahead and subtract them. So 0.7486 minus 0.2514. The difference is going to be the area in the middle, which is 0.4972. 0.4972. So about 49% chances, almost 50% chances, that if you randomly select an individual from the crowd, their IQ will be between 90 and 110. So 49.72% or 50% chances, high probability that you randomly select an individual and their IQ will be between 90 and 110, the average intelligence. Part C is pretty similar, so I'm going to skip part C, similar to part B. Part D, calculate the probability of IQ being less than 90. That is going to be similar. Let's go ahead and do part D really quick. Probability of IQ less than 90, that would be probability of z-score. We already found the z-score for 90 in the previous example. Did we? Yeah, negative 0.67. So what's the probability of the IQ less than 90? We're probably randomly selecting an individual whose IQ is less than 90. So I converted the 90 into standard score, which is called z-score. And the z-score turns out to be negative 0.67. And I'm looking for area to the left, because we want to find the probability of finding somebody whose intelligence is less than, or IQ is less than 90. So, and we just found this in the last problem. So 0.2514. I'm going to steal the answer from there because it's right there, 0.2514. So about 25% chances that you randomly select an individual and their IQ will be less than 90. Okay, now let's check out part E. Part E says calculate the 60th percentile. 60th percentile, we talked about percentiles in chapter number 3. 60th percentile is the one that has 60% area to its left. 60% change to the decimal is 0.6000. Am I going to look into positive z-scores or negative z-scores? Oh, well, I know it's going to be a positive z-score because it's got 60% area to its left, okay? In the positive z-scores, let's look for 60% area. Let's look for 60% area to the left. So in the positive z-scores, 0.60 in the body of the table. 0.60. 0.62 is here. Looks like in between these two, 0.6026 and 0.5987. Seems like 0.5987 is closer, so my z-score would be 0.2. 0.25. So the z-score comes out to be 0.25, and we're looking for the data value. So z is x minus mu over sigma, which is 0.25 equals x minus 100 over 15. Go ahead and solve this equation. We're going to multiply both sides with 15 to solve it. That's the first step. 15 times 0.25 is 3.75. 3.75 is x minus 100, and then I add 100 to both sides, so that would be 103.75. So the z-score, or the IQ score, this is the data value IQ score. So the IQ score that has 60% to the left is 103.75, or we can say the IQ score is approximately 104. Okay. Next, we can look at part G. Find the IQ score separating top 10% from the others. Okay, G. The top 10% are going to be here. They have 10% area to its right. Well, if it's got 10% area to the right, how much area to the left? 90% area to the left. So I'm going to write it using 4 decimal places in the positive z-scores. I'm looking for the z-score that has 90% area to its left. 90% in the positive z-scores, 0.90. Let's see what's the closest. If we don't have 0.90 here, then we'll go with the one that's closest. 0.9015, 0.8997. Seems like this one is the one that's closest. So my z-score will be 1.28. Okay, 1.28 is my z-score that has 90% area to its left. Okay, so data value minus mean divided by standard deviation. 1.28 is x minus 100 divided by 15. So to solve it, first multiply 1.28 with 15, and that's 19.2. X minus 100, and x comes out to be 119.2. X turns out to be 119.2, because from here x turns out to be 100 plus 19.2, which is 119.2. We can say the IQ score that separates is approximately 120 or 119. 119 is the IQ score that separates the top 10% from bottom 90%. That's all.